Bismillahirrahmanirrahim. Let's begin our chapter 8, entitled as Conservation of Energy. So, first thing first, we need to know the system that we are going to consider, the model that we're going to consider in our syllabus. So, actually, okay, in terms of energy, the one that is so common to us is actually the non-isolated system. Non-isolated system means that the energy of the system, right, crosses the boundary of the system itself during some time interval due to interaction with the environment. So let's consider this is a model of a system. Consists of, within the system, the energy consists of three types of energy. The most common, kinetic energy, potential energy, and internal energy. And this is our system, right? And we have boundary here, right? Outside here considered as the environment, right? If there is a transfer or change in energy between the system to the outside or the environment, probably in terms of kinetic energy or potential energy or heat transfer, right? Any kind of it, right? So means that our system is interacting with the environment, and some of the energy crosses a boundary. It could be from the system into the environment, or from the environment, okay, into the system also can be, right? So if there is any interaction in terms of energy crosses between the boundary of the system and the environment, we say this kind of system known as non-isolated system. Alright, this is a common in our daily life actually. Okay, for example, okay, where we have in this figure A, energy is transferred to the block by work done by the hand. Energy for a radio or also can be used as a clock here. Okay, energy leaves the radio from the speaker by mechanical wave. There is a transfer of energy from the system to the environment. And see here we have a mug consists of hot coffee. Okay, energy transferred to the handle of the spoon by heat. Okay, and for this case, okay, we have energy enters the automobile gas tank by metal transfer, because we are transferring the fuel into, okay, the tank of our vehicle. And for this case, okay, hair dryer here, energy enters the hair dryer by electrical transmission. And last one, energy leaves the light bulb by electromagnetic radiation, okay, where we have lights. So energy is always conserved, we know this, okay. This is the law that created by Allah Ta'ala. Okay, as a Muslim, we believe that Allah is the sources of the energy. Okay, we cannot create, okay, or we cannot destroy either the energy. We only can have transform of energy or change in method of delivering or using the energy. That is how we know that energy is always conserved, means that energy final must be equivalent to energy initial, or it only can cross boundary and change in form. Alright, so change in energy of a system must equivalent to the sum of the transfer mechanism, okay, that we discussed in previous slide just now. So what kind of energy consists within a system? What kind of change of energy? We can have change in kinetic energy. We also can have a change in potential energy, or in terms of change in internal energy of a system. Must equivalent to the sum of transfer mechanism. What can we have? Work done, heat, okay, transfer of mechanical wave, Okay, transfer of matter transfer. Okay, transfer in terms of electrical transmission or transfer of electromagnetic radiation. If only change in system is speed of one or more components, okay, work kinetic energy theorem, if you still remember, delta K is equivalent to W applicable. Okay, if the one that change, okay, is about speed only, then we can have this kind of work kinetic energy theorem to be used to solve any kind of problem related to that. Alright, so if we want to visualize in terms of the sum of the transfer, it could be in terms of work done in or out. Okay, heat transfer into or out, mechanical wave, electromagnetic radiation, electrical transmission, or also matter transfer. The change in total amount of energy, okay, in the system is equals to the total amount of energy that crosses the boundary of the system. That is the meaning of the sum of the transfer within the system and the environment. Okay, concept 2, example 8.1, reducing the conservation of energy equation in specific situation. When using the energy conservation equation to solve a problem, the following steps should be remembered. First, you need to define your system. Which one is the system? Second, you need to identify the beginning and end of the time interval of interest. You need to know, okay, where to begin, when to put an end to the process. Identify initial and final configuration of the system, position of objects in gravitational situation, extension of spring, and etc. And assign appropriate reference value of potential energy. You have to have a setting axis properly, means write the energy conservation of equation, eliminating or setting terms equals to the zero that do not apply in the situation. Okay, so let's take a look on how to do this. Right, consider the following examples. For each example, the system is provided and the time interval is from before the device is turned on until it has been operating for a few moments. Right. If we're talking about our television set, okay, the change in we don't have change in potential energy. We also don't have the change in kinetic energy. Our TV is not moving or having a change in height. Okay, but there is internal energy change due to what? Due to the transfer of heat. There is no work done. Also due to the transfer of mechanical wave. Okay, but there is no transfer of matter, isn't it? And then also there is electrical transmission. Okay, and also electromagnetic radiation. That is how finally we can simplify the original equation into this. That is the meaning, the steps must be taken in previous slide. Okay, so let's take a look on this. Your gasoline powered lawnmower. Okay, the time interval includes the process of filling the tank with gasoline. So this is the original. Okay, but then, okay, so we are talking about lawnmower. There is movement, change in kinetic energy. There is probably change in position as well, or height. There is a change in potential energy. Definitely there is a change in internal energy. Okay, must be there is a work done by the lawnmower, isn't it? Must be there is a heat transfer of mechanical wave, transfer of matter. Okay, but there is no electrical transmission. We are not using power supply, right? Also, we don't have the transfer in terms of electromagnetic radiation. There is no light transfer in or out from our system. So finally, we can have this equation as the simplified version of the situation for gasoline powered lawnmower. Okay, then see a cup of tea being warmed in a microwave. Okay, so there is no kinetic energy change, there is no potential energy change, but there is internal energy change. Okay, there is no work done, there is a heat transfer, no mechanical wave, no matter transfer, no electric transfer, but yes, there is electromagnetic radiation because we are using microwave. So finally, our equation is going to be simplified into this version. Next one. Now, let's take a look on the isolated system in terms of energy. So, this is a common diagram that you've seen in previous topic, right? Talking about change in position or related to change in potential energy due to the gravity. So, the book is held at rest here and then released. So, now at lower position, the book is moving and has kinetic energy, is in motion. So, in terms of change in kinetic energy, yes, we do have. In terms of change of potential energy due to the gravity, yes, we do have change in height. Okay, mass equals to 0. Okay, so transformation mechanism work done on book within system by the gravitational force. In other words, when we have this, because change in gravitational or potential energy due to gravitational is actually equivalent to the negative delta K. Conservation of mechanical energy. So within mechanical energy, we have two kinds of energy, kinetic and also potential. Talking about conservation, it means that E mechanical initial must equivalent to E mechanical final. We cannot have addition of it or reduction of it. It must be equals. That is how change in mechanical energy is equivalent to 0, because change in is mechanical energy final minus mechanical energy initial. It must equivalent to 0. So substituting the information that E mechanical has two kind of, okay, into this equation, it brings us to this. Alright. So if we collect the same item, all the final item here, all the initial item here, then we can have this kind of form. This is in terms of, okay, the real formula of them is actually for K is half mv squared. We already derived this. How come it's half mv squared? Okay, and then for potential energy is mgy. Right. This is for the term of final. Here is for the term of initial. Alright, and then E mechanical plus E internal must equivalent to E total initial must equivalent to E total final. That is how delta E of the system equivalent to 0. Alright. So isolated system, if you want to have a visualization how the isolated system is considered for energy. Okay, let's say this is our system. This is a boundary. Within a system, we have kinetic energy, potential energy, and internal energy. The total amount of the energy in the system is constant. The initial state, the E initial, E mechanical initial, equivalent to E mechanical final. That is the meaning. Energy transforms among the three possible types. Okay, this is a possible. But then, if you're talking about isolated system, delta E of the system is equivalent to 0. It means that there is no transfer in or out of the system. Okay, everything is conserved. If no non-conservative forces act, there is no friction. Okay, non-conservative does not exist. Okay, delta E mechanical must equivalent to 0. Okay, delta E mechanical must equivalent to 0. So we need to highlight no conservative forces, okay? Then this condition is applicable. Example 8.2, ball in free fall. A ball of mass m is dropped from a height h above the ground as shown in the figure. A. Neglecting air resistance. Determine the speed of the ball when it is at a height y above the ground. Choose the system as the ball and the earth. Right. So, initially, the ball has h height, y initial. And it has potential energy in terms of gravity, initial, equivalent to mgh. And the kinetic energy is equivalent to 0. Why? It starts from rest. Because, okay, drop. So V here, V initial here, equivalent to 0. That is Y. Okay then. The position here, whenever the ball is reaching Y position, okay, after it is dropped from H, okay, Y initial. So now your Y final is Y from ground, and potential energy in terms of gravity final is equivalent to mgy. And here we do have, the ball do have a kinetic energy because it do have V here, so it's equivalent to half mv final squared. Whenever the ball reach ground, now the Y here is 0, therefore the UG also 0. Right. So, okay, delta K plus delta UG equivalent to 0. Okay, we have half mv squared V final squared minus half mv initial squared, but V initial is 0. This is actually half mv initial squared, but our V initial is 0. Okay, and then delta U must be U final mgy. Okay, this is our Y final, this is U final minus U initial, okay? Okay, and U initial is mgh, mass equivalent to 0. So, from here, we can rearrange the equation and put our interest, our V final is equivalent to 2g h minus y. M is cancelled out because, okay, if you see here, half m V final squared equivalent to mgh minus mgy. So my dear, we do have m for both sides, okay, for all parties. So we can simplify the term in term of this. So bring the cut that part. So then multiple both sides with 2. Then you are going to have, right, V final squared equivalent to 2g h minus 2gy. Might as well we simplify the version. 2g h minus y. This is how we have the formula. And if we're talking about V final only, then square root everything here. Okay. B. Alright, find the speed of the ball again at height y by choosing the ball as the system only. Alright, so if I consider only the ball, not the earth, so it will be delta K plus W. Okay, there is no more delta UG because we are only considering the ball as the system. So change in kinetic energy is equivalent to K final, half mv final squared, minus K initial. Initially, the V is 0, as I stated before, is equivalent to work done. Okay, work done by what? By the gravity. Gravity is the one that caused the ball to move downward. That is how we know delta K equivalent to W. And work done by the gravity is the product of Fg dot delta R. Delta R is change in position vector. So we have mg is negative because it's downward. Weight is always downward, right? This is weight. Okay, so along negative j, then times delta y, also in j. So since it's a dot product, so j dot j becomes 1. So we have mg delta y. We do have negative, okay? All right, so negative here. Okay, then we have within delta y itself must be y final. This one, delta y, it means y final minus y initial, right? So our y final is y, our y initial is h. Okay, so if we want to rearrange the negative, also can be done. So swap this one, right? Okay, and then from here, again, rearrange the equation. You will have this kind of formula. So if you compare this one to this one, it's actually the same, right? So we managed to get the same equation, even though we are referring to different system. Okay, what if the ball were thrown downward from its highest position with a speed v initial, right? What would its speed be at height y? Okay, so if there is a v initial, the kinetic energy is not zero anymore, isn't it? We do have half m v initial squared because it's thrown downward, okay? We do have v initial. So again, we are going to repeat the same method of the calculation, okay, whereby you have to have half m v final squared minus half m v initial squared. This is delta k plus delta u mg y final minus mg y initial is equivalent to 0. This is our delta u. If you consider ball earth system, okay, then rearrange this, you will get this formula. Okay, now let's move to example 8.3, a grand entrance. You are part of the stage crew for a theatrical company and are designing an apparatus to support an actor of mass 65 kilogram who is to fly down to the stage during the performance of a play. You attach the actor's harness to a 130 kilogram sandbag by means of a lightweight steel cable running smoothly over two frictionless pulleys as in the figure. You need 3 meters of cable between the harness and the nearest pulley so that the pulley can be hidden behind a curtain. Okay, so this is the situation explained by the statements here. Okay, the actor here, we have the R here, we have the sandbag here, this is the angle, this is the Y initial of the actor, and finally it will reach a Y final here, right? For the apparatus to work successfully, the sandbag must never lift above the floor and the actor swing from above the stage to the floor. Let us call the initial angle that the actor's cable makes with the vertical theta What is the maximum value data can have before the sandbag list off the floor? Okay. Now, what can we have here in terms of formula? Must be delta K of the actor here plus delta U due to the gravity equivalent to 0. So in terms of actor, half mv actor v final squared. Okay, this is K final. This is our K final minus K initial. Our K initial is 0. Why is it 0? Because V initial of the actor is 0. Okay, and then delta U is U final. Here is U final minus U initial. So we have mg Y final minus mg Y initial. Right, which is this is actually mg delta y, isn't it? Then equivalent to 0. So the m can be cancelled out, already shown in the previous equation. So what can we have here is v final squared of the actor equivalent to 2g times y final minus y initial. So y final minus y initial, also known as delta y. Okay, so based on this diagram, trigonometry diagram here, we can see here that okay, delta y, okay, the height here, okay, the difference between y final and y initial here, which is the delta y, is equivalent also to r minus, okay, r cos theta. What is r? If we can transfer the information of r is here up to this. The green color is here is r. So r, okay, minus r cos theta is actually equivalent to delta y, or y final minus y initial, which is this one. Okay, so from here we can simplify in terms of trigonometry here to figure out the formula for theta. So we have here delta y, right? Okay, substitute this into this equation, then you will get v final squared equivalent to 2g times 1 minus cos theta. Alright, the next one, okay, we are going to consider the forces. Okay, now we are going to consider the position whenever the actor already at this position at y final, because whenever the actor is at y final, then the tension is transferred to the sandbag, isn't it? So at this moment we do have the tension and then also weight of the actor. Sum of Fy is equivalent to T minus T positive minus M of the actor, mg of the actor. Mass equivalent to MAC, because the actor is swinging in circular path, taking a circular path. T is equivalent to M actor times with a G plus, okay, M actor V final squared over R. So this is AC, okay. So and we know that, okay, for the sandbag itself, the tension experienced by the sandbag, okay, mass equivalent to the weight of it. Okay, then we may substitute weight of the sandbag is equivalent to T, then the rest of this, okay, remain here, right? And this is from the previous, okay, of V final equation. Then you substitute everything here, okay, you see we can simplify the terms, right? And finally substitute the M of the actor and also the sandbag, okay, then you will have cos theta equivalent to 0.5, where give you theta equivalent to 60 degree, right? Example 8.4, the spring-loaded pop gun. The launching mechanism of a pop gun consists of a trigger release spring. Okay, the spring is compressed to a position YA and the trigger is fired. Right, the projectile of mass M rises to a position YC. Okay, above the position at which leave the spring, indicated in the figure as position YB equivalent to 0. Consider a firing of the gun for which M is equivalent to 35 gram, YA is equivalent to negative 0.12 meter, and YC is equivalent to 20 above the Y0 or YB here. Neglecting all resistive forces, determine the spring constant. Okay, so by using energy concept, delta K plus delta U of the spring, we have two kind of potential energy here. One of it due to the gravity because changing in position or height. The other one is due to the spring because the spring being compressed. That is a change in potential energy of the spring itself, equivalent to 0. Kinetic energy start from rest and finally also at rest, because maximum height it will stop a moment, so both of it will be 0. Kinetic energy initial 0, kinetic energy final 0, and potential energy final is mg y final, which is c yc, minus potential energy initial, which is mg ya. Okay, plus, okay, finally the U in the spring is 0 because the spring is not compressed anymore. So because the X is 0, no compression, okay? So U final of the spring 0, U initial of the spring, yes, we do have value which is half kx square. The X is the compression, okay? Equivalent to 0. So from here, rearrange, okay, the position of the items, okay, make the K as our interest as the title, then substitute the rest of the information, then you will get your K 958 Newton per meter. B. Find the speed of the projectile as it moves through the equilibrium position B, okay, of the spring. Again, we are going to repeat this, but of course, okay, half mv final will be v at B, okay, which is not 0, okay, it is in motion, right? Minus kinetic energy initial, which is 0, start from rest, okay, plus, okay, U gravity final, because at y equivalent to 0 is equivalent to 0, okay, and then minus mg y initial, which is from A at ya, right? This is not 0. This one yb is 0, right? That is why this value becomes 0. Plus, okay, potential energy spring final, finally there is no compression, okay, so it's 0. The x is 0 or the y is 0, minus the potential energy spring initial, which is half kx squared. This is a compression, okay, equivalent to 0. Then rearrange the equation, make the VB as our interest because the question asking for this, and the rest substitute the values. You will get, not to forget that your YA is negative. You have to put the negative sign in your calculation, okay, because it has meaning it's below YB, right? Then finally you will get your answer 19.8 meter per second. That is V at position B.